Hello everyone, welcome to another MeTTa tutorial. In this tutorial we're going to be seeing how to implement certain knowledge representation in MeTTa and write some simple functions. So let's get started. The first thing we need to know about MeTTa is whatever code you write, it has to be included in a bracket. Of course you can write something outside of the bracket, but that won't be that useful. So most of the things you'll be writing will be included in a bracket, whether it's a function, whether it's simple information storing, anything. So let's try to see first how to represent certain information in a MeTTa. Let's say we want to store a person's information inside our code. So the first thing we can do is just type in his information in a tuple, like a tuple. So we can write his name. Let's say his name is Adam. Let's say he's 23 years old, and let's say, well, he has a salary of $2,000. So this could be one information, and we can also add his gender as well. So we can have his information stored in a single tuple. So this whole information will be stored as a graph within our atom space. So let me tell you what an atom space is. An atom space is basically like a database inside MeTTa. So whatever you write in a single file will be stored or will be treated as an atom space. So you can also create your own atom space, but we won't be covering that in this tutorial. So basically what we are writing here in a single tuple is being stored in an atom space or in the current file, which is going to be treated like an atom space. So we are storing this whole information in a tuple as an atom or as a single atom or as a single information in this atom space. So we have the person's name, person's age, salary, and his gender. So we can have multiple entries. We can copy and paste this, and we can have different entries for different people. Let's say someone else as Monica, whose age could be 21, whose salary could be $500, and she is a female. So we can have a lot of information like this. So you don't need any other fancy stuff. It's just simple. You just write what you want to store and put it in a single bracket. That's all you need to know. So you can even include some nested brackets here. It doesn't have to be a single atom or a single thing you're writing here. So for example, if I want to include the person's first name and last name, I can say Adam James and include it in another nested tuple. So this is also possible. So as long as you're writing things in a way that matches the bracket, then it should be good for storing information. But if I, for example, turn off this bracket, then that could be an issue because the brackets don't match. So as long as you have a balanced bracket, whenever you want to store information, then it's pretty easy and simple. So you can store information like this. Let's update his name and change it back to someone else. Let's say Joe. And let's update his age to be 30. And add one more girl in here, Pam, who's going to be, let's increase their ages, 50 and 60. So Pam would be a female with $3,000 salary. So basically what we try to do here is represent 4 people's detail or 4 people's information in a single tuple. So each of them are stored in a single tuple, and all these 4 entries could be considered as an entry for a database. So you can see these 4 different entries as 4 different columns inside a single database if it was an SQL database. But the only difference here is we're just storing them in a tuple. As long as we're including them in a bracket, then the MeTTa can treat them as a valid MeTTa code or a valid MeTTa code written or representation. But we're just writing this to store information. That's all. So you can store information like this, but now we want to create some kinds of relationships between these people, some kinds of graph. So we can create some meaningful connections. So in this video, we're trying to see how to represent a family relationship inside MeTTa code. So we need to store additional information. We're still storing information, but we're trying to make it more meaningful. So we can somehow, for example, say Joe is parent of Adam. So this is another information that we are putting in. So we're basically saying the person Joe is a parent of Adam. So we're creating a graph entry that's connecting two nodes, which is Joe and Adam, using another H, which is parent. You can think of it like that, or you can just think of it as a database entry where we're putting in a string of Joe is parent of Adam, and that's it. And we can add more information like Pam is also parent of Adam, and we can paste this again and add the same entry for Monica. So basically we're trying to say that Joe and Pam are the parents of Adam, and Joe and Pam are also the parents of Monica. So we can also have more people here, but currently it's not necessary. So this is how you can define some sort of relationships between unexisting nodes in your graph or in your database in MeTTa. So now, if after storing this information inside our code, we need a way to retrieve them, or we need a way to query them or search them. So for another database, for an SQL database, which is basically like your SQL query, or for another like a graph database like Neo4j, it could be a Cypher query. But for MeTTa, we're going to write the query using the language itself. So we'll try to match certain information from these stored facts or data. So the syntax is going to be a little bit different, but it's going to be enclosed in a bracket as usual, and we're going to call a function called match. So whenever you have a predefined function, the function name comes first. So you write the function name first, which is the function name is match, and you give it certain parameters. This match function takes 3 parameters, excuse me. So each of them have their own meaning. The first one, we're going to give it the atom space. So if you remember, I told you that a single file can be considered as an atom space, or you can also create your own atom space, but you store information in an atom space. So when you want to query that information, we have to give the function which atom space we're referring to. So we can write like something like self, for example. Self is always a predefined atom space. You don't need to create a new atom space to access this. But self refers to the current file as a space or as a database. So when you write ampersand self, you're basically saying that query certain things from this file. So treat this file that this match is being called in, and treat it like an atom space, and query the match that, or the run my query inside this, or run my query on this database. That's the main idea. So we have this database or the atom space we want to run in, and we will give it what kind of data we want. So the kind of data we want could be wrapped in a bracket, or we can just say $X. So basically what this is basically like a variable. So we want to query our database and store all our information on this variable. So what we're saying is, if we don't specify anything, if we're just saying $X, which means basically trying to say, try retrieving everything in this database. So when we write $X is a variable, but when we don't specify any specific format, then we're just saying match everything, or give me everything inside this database. So that will become a bit more clearer when we see what I mean by specific pattern or a specific order. So the last parameter is going to be what do we want to return after calling this function. So we can write any MeTTa code in here, but for the time being, I'm going to use a string representation. What I'll say is everything in the database. Everything in the database is X, and make sure to wrap it in a single bracket, because if you don't wrap it in a single bracket, it's going to treat it as a separate input. So if I remove the bracket, for example, this is going to be one input and this is going to be another input. But if I wrap this in a single bracket, it would be treated as if this is a single entry. So that's what we want to do. And then after finishing this, we need to make sure that there is an exclamation mark in the front. So in a previous video, if you remember, I told you that you can use this exclamation mark and not to forget it, but I'll tell you its purpose. The main purpose of this exclamation mark is to differentiate between the brackets we are storing in the atom space and the brackets we actually want to run or execute. So it's basically differentiating what do you want to store and what you want to run. So whatever you want to run, you have to add this exclamation mark on it. Whatever you don't want to run, you just want to store it as a fact, you won't add those exclamation marks. So if you forget this exclamation mark, there's nothing that is going to be run. This whole function call is going to be stored in the space and wait for some other function to match it or to search and find it. So it won't going to be run. But if it's not run, if you want it to run, you will add this exclamation mark and everything should go as we want it. So let's activate our virtual environment and see our progress so far. Let's type in MeTTa family.meta. So as you can see, there are some additional information that are already stored in our space, and it's basically retrieving everything it can find. That's why we were seeing this gigantic output here. So instead of just running it as $X without giving it any specific pattern, let's try giving it a specific pattern. So if we say $X, there are things that we are not storing explicitly in this predefined ampersand subspace, like for example certain standard library functions or certain constants that we can use or certain documentation informations. We're not explicitly putting it, but there's already inside the space added by the programmers of the language. But in order to match our own data, we can give it the pattern. So what I mean by the pattern is, what does the data look like? So when I say pattern and when I say pattern matching, all I'm trying to say is what kind of data do we want to retrieve? So for this case, for example, we have a people's data. So this people's data has a certain pattern. The first one is a name, the second one is their age, then their salary, then their gender. So we basically have 4 columns. So what do you want the data to be retrieved have certain patterns. For example, we can say, I want to retrieve the information of Adam. I don't know his age, I don't know his salary, and I don't know his gender. Or I don't want to specify those. So basically what we're trying to say is match me or try to find anybody in the atom space named Adam and follow the other patterns as well. So we have to give the other patterns even if we're not exactly using them in our pattern matching. So when we do this, then this X will be corresponding to the age of Adam. So we can say in here something meaningful as Adam is like X years old. And let's try to run this. So as you can see, now we have outputted Adam is 23 years old. So let me clear that to make sure everything is visible enough. Yeah, so Adam is 23 years old. So X will now correspond to the value at this specific location when we store it in our database. So what will happen if we have more than one Adam? What would happen if we have like an Adam with, let's say, 33 years old, and he has the exact other same entry? So when we run this match query, we'll find 2 entries. The first one would be an Adam with 33 years old. The second one would be the Adam with 23 years old. So if we want the Adam with the 23-year-old, we can say, I want the Adam with the 23 years old, who's 23 years old. So we can say Adam is 23 years old and he has $Y dollars of salary. And we can change their salary so that we can differentiate which is which. Okay, so let's run this now. And it's basically saying Adam is, oh, we don't have X anymore. We are replacing it with 23, so we need to change that. Adam is 23 years old. Adam is 23 years old and he has $2,000 of salary. So whatever we're trying to match here, we can use it in the second query that we're doing here. And you don't even need to wrap it in a single bracket. You can just return, I want just to return $Y and $G. So $Y stands for the salary because that's what we stored in our current database, and $G stands for his gender. And if you change these positions, basically the whole matching process also is going to match a different thing. So previously $Y was his salary, but now $Y is going to be his gender and $G is going to be his salary. They're going to be exchanged. So this pattern is basically trying to match what is stored in our database or in our Atom space that we can retrieve and somehow organize however we want or return however we want it to use or however we want it to be displayed. So let's run this and we see it's giving us male 2000. So that's because we wrapped it in a bracket and we need to wrap it in a bracket, otherwise we can't return two things. If I remove this bracket, it's going to show some kind of error. Yeah, error, incorrect number of arguments because it's expecting 3 arguments, but we're giving it 4. So we need to wrap it in a bracket and this is going to output in a single bracket and it's going to be male 2000. So if we return it to how it was before, then the order should change. It's going to be 2000 male because $Y is going now to match to its salary and his salary, and $G is going to match to his gender. So that's how we can match into the space. So when you match the space, we can write other types of query too. So let's try to match who is Adam's parent. So we don't know his parent, we can say $Y, but we want to find the information, the parent information of Adam, let's say. So when we want to find the parent information of Adam, we can write $Y is parent of Adam. And then we can just return the $Y. That's the only thing we want to return. So let's run this and let's comment the others out. In MeTTa, in order to comment a certain code, you just need to type semicolon before the code. That should do the trick. And let's comment the other ports out and let's run the ones we want. Okay, it's showing some kind of error. Why is that? Oh, there's an additional bracket here, my bad. Yeah, so it gives us two informations. Pam and Joe are the parent of Adam. So that's basically what it's returning. And that's the truth because we stored in our space that Adam's parents are Joe and Pam. So that's how we can match. Or we can also do the reverse. We can say who is Joe a parent to? And let's say we don't know who Joe is parent to. Or I can just copy this. We can say, I want to retrieve who Joe is parent to. So we can do the reverse as well. So if you run the code, now we're getting Adam and Monica. So if you see Joe is a parent to Adam and Joe is also a parent to Monica. So it's giving us two of them as well. So that's how we can do a pattern match. So basically what you're trying to do is giving it the pattern of the data and you can give it some unknowns. For example, this $Y is a variable to store the unknowns of the pattern. I know what I'm looking for is a parent. That's why this is parent of is already written, not a variable. I know that I want to look who Joe is parent to, but I don't know who his childs are, or I want to know who his childs are basically. That's what we're saying. So it retrieves the child, and what you can return here however you want it. You don't need to return the variable only. You can return the variable only if it's a single variable. If it's more than one variable, you need to enclose it in a bracket. But if it's neither of them and you can just want to return however you want, you can even do certain operations over here if you have some functions, or if you want to do another match here. So maybe let's just see that and move on to the next thing. So for example, if you want to have the full information of the child, here we're just returning their names basically, because that's why we're storing in the parent relationship. But let's say we want to know the full information of the child. So what we can do is call another match function in here. So as I told you, in the second one, we can run another function call. So we can say $y, which is how we stored the person's information. If you remember, the first one is going to be their name, and the second one is their age. We can say $A for that will correspond to their name, $S to the salary, and $G to their gender. So we can do another match that match this pattern. So let's put this in another match function call. And remember, the first argument is going to be the space, which is at &self, referring to the current space or to the current file. And we can give it the query that we just copied, and we can return the whole information. So we can just return the whole variable over here. So now if we run this function, there is another bracket over here. Now if we run this function, we should get their whole information. Adam is a 23-year-old male, and there's another Adam with a 33-year-old male, and Monica, 21-year-old male. So there are two Adams. So that's because we added another Adam here. We can just comment that out. Okay, so now we should have only two Adams. So this way you can recursively, or you can add another function as a return type for the match function that you're calling. So basically that's what you can do. So yeah, this is how you can match, and I think we can move on to creating certain functions. So one thing you need to know, MeTTa is like a functional paradigm programming language. It's not purely functional, it's also a logical functional programming language. It's sort of like a logical functional programming language, which means you can write some logical statements inside it, and you can also write some functional programming logic inside it. So what I mean by functional is whatever you want to do, it has to be in a function. So when you see when we want to query the space, we have to call the function match, and that is a function. And this function's return could also be another function. That's why we are basically calling another function over here. So it's trying to return another function call. So maybe you can just look into how functional programming works in a separate topic. So I won't go much further inside it. But for now, you can just think of it as another function call. So inside match, as a return, in the place of returning match, we are calling another function, which is match itself with a different parameter. So another thing you might need to know about match is whatever you're trying to pattern match here, this variable is only accessible as long as you're in the match function. So in the match function call. So if I go out of match and I try to print the $y, or maybe let's wrap it in a bracket in the $y, the MeTTa interpreter is not going to know what $y means. So it's going to be printing $y itself. It's not going to be printing anything. So whatever you're trying to match here is only accessible here, which means in the third parameter. So whatever you're trying to match in the second parameter will only be available in the third parameter. So its context is limited. That's why most of the time you'll write some other function here if you want some programming logic to be done. Or you need to store this whole match variables output on this whole match functions call output in a certain variable and returning the result of $y from this match function first. And we can maybe see that in a different video, or you can also find it in the documentation. So everything that I'm showing you here, this is just a quick starter. Every detail you found in the documentation, we'll try to link it in the description, and you'll be able to see more details over there. This is just to write some code to get you started. Okay, so let's move on. Let's clean up the code a little bit. So, okay, what else can we do? So, one thing that you can assume about doing is we have information stored in our database or in our graph or in our atom space, whatever you want to call it. But I'm going to call it in our atom space from now on. There is an information that we don't need to store, but we can infer. So that information is basically the relationship between Monica and Adam. We can store the relationship between Monica and Adam, but that would be redundant. This is only 4 people, but imagine if you have like 100 or 1,000 people in your database, in your atom space, then that would be tiresome. But you can infer this information. So how can you infer this information? Basically, you just need to think a little bit. When will I say 2 people are siblings? 2 people will be siblings if their parents are the same. So what you can do is like write some sort of function that basically tries to execute this rule, or try to retrieve from our database the people who are going to match this rule. So the rule is going to be X is Y's sibling if, let's say, N is parent of X and N is parent of Y. So if we can find a parent N, which is a common parent for X and for Y, then we can say that these 2 people are siblings. So, or we can do it the other way. We can give a person X and try to retrieve that person's sibling, or try to find that person's other sibling. So we can write some function like this. So for a function definition, you're going to start your, as usual, with a bracket, and you can write an equals to over here. And this basically tells that if you find this kind of function definition, try to execute the one at the second. So this is the basic pattern or structure of function definition. You write the function name and the function parameter in the first one, and you write the function logic in the second one. So let's say the function says is sibling, and takes X and takes Y. So basically it tries to find if these guys are siblings or not. And we can do it in a try to match at self, trying to retrieve the information. Let's just format it a little bit so that we can see better. To match at self, we want to find a $n that is a parent of $x. So this $x is actually going to be replaced by the actual $x, which is right here. So if the $x is this sibling function called with another parameter like Adam, for example, this $x right here is going to be replaced by Adam because we're using the same variable name. If we don't want this $x to be replaced by Adam, we need to give it a different name than the one in the argument. We can, for example, type it like x1. Then that would be matching from our space. But right now, we want this $x to come from the function's argument. So we're going to write as $x. And then we want to make sure that this parent $n is the same for $y too. So what we want to do is do another match query at the self, but we want to find the $n that is also a parent of $y. So this is basically what we're trying to do. So we're trying to find the $n, which is going to be the parent of $y. So we're basically trying to find another parent that's going to match $x and $y. So after completing this, we're going to return, if there is a match, we're going to return true. So If there is no match, we're going to return empty because we didn't find anyone that matched this this exact rule. So $X and $Y are siblings if they share the same parent when we represent that in our query. So let me go through it once more. We have a match query and we're trying to find $N, which is the parent of $X. So $X is the first person in our argument. So we're trying to find who are the parents of $X. And then after we finished with that, we're going to match and we're going to do another match query within this match query. So make sure that this match query is nested. Don't forget they're nested, or this true should be over here. Don't forget they're nested. So we're going to do another nested match query, and we're going to use the same atom space at self, but now this $N is going to come from the first match query. So whatever this first match query matched is going to come to the second match query, and we're trying to do another match query, which is try to find a parent $N who could be a parent to Y. So let's see it in an example. For instance, let's say we are calling the isSibling function with, let me turn off the terminal and see it more, give us more space. So if we call the isSibling with Adam and Monica, what this function tries to do is it tries to match $N, who could be a parent of Adam, because Adam is the first argument, right? We gave Adam. So we're here trying to replace the first argument with in the appropriate query. So we're going to match this query. So who is the parent of Adam? So the parent of Adam are Joe and Pam. So this $N is going to be sort of a list of two people, Joe and Pam. So this function first tries to return Joe and Pam. So $N is going to be a list and it's going to be passed to the second match query. Because remember, whatever is in the third query has access to the match result. So the match stored the result on the variable $N. It didn't store on the variable $X because we replaced $X with Adam because that was the argument of the function. And then in the second match query, what we're trying to search is find this $N, find a person $Y that matches this $N's parents. But remember, $N is now a list of two people, so we are not actually trying to search into the space and store the information on $N. We're just trying to search on the space that satisfies these two conditions. So $N is either Joe or Pam, but $Y is actually going to be Monica. So we can give Monica as $Y. So what we're trying to do here is try to find people whose parent is Joe and whose child is Monica. We're basically trying to search, is there an entry Joe is parent of Monica in our space? That's what we're looking for, but that's not the only thing that we're looking for. But because if you remember, $N is a list, so we're also looking for, is there an entry in our space where Pam is the parent of Monica? So it will return an exact entry, or it will return true for each of these corresponding results. So that's basically what we're trying to search for in our space. So if there is an entry of Joe is a parent of Monica, it's going to return true. Or if there is an entry of Pam is a parent of Monica, it's going to return true. If both of them are existing in our space, it will return two truths. But if neither of them exists, it will just return an empty list, so that we know the sibling information or relationship is not existent in our space. So let's try running this siblings function. Is Adam sibling of Monica? So remember, when we call a function, we put the function name first and then put the arguments continuously. And we wrap it all in a bracket. We wrap it all together in a bracket. Okay, so let's bring our terminal up and run this. So as we expected, we found 2 truths. So what if we write some other information like is Adam and Pam siblings? We get empty. So that means these 2 people are not siblings. They're not siblings, which is which is something that's true because we didn't specify it that way. Okay, so we can also write something like is parent, which is basically a simple function actually, but it can help us understand things more easily. So let's just start from scratch. So a function, as you remember, has 2 parts. The first part is going to be its name and the parameter definition. The second one is going to be the actual function logic. And we know something is a function definition because of this equals to sign in the beginning. So let's try to run this. So we're trying to match from our space that x is a parent of y. So if there is an entry where x is the parent of y, we're going to return true. So you can just run this. Oh, I didn't call the function, my bad. So we're trying to find an x that is a parent of y. So if there is an x that is exactly a parent of y, then this should return true. But if that's not the case, it won't return true. It will just return empty like before. So Adam is not a parent of Joe, so this is going to return empty. But let's try to reverse them. Let's say, is Joe a parent of Adam? And it's returning true because Joe is indeed a parent of Adam as we stored it in our database or in our atom space. So that's how you can call and define some simple functions on your database. So let's just put this back and run it one more time. Yeah, we can see both of the functions result here. So that's basically how we can store some certain small informations in our database or in our atom space, and then write some logic functions that can do certain matching and querying things on the space and retrieve certain information or certain meaningful information. And you can also rewrite this function in a way that it returns the siblings instead of returning true or false every time. But you need to know how to store variables and that kind of thing from the documentation, so it might take you some more steps than this. So yeah, that's basically it. That's how you can represent a family in our database and use some functions to call and do certain logics for you. And thank you. I'll see you in the next tutorial, and I will try to see a small thing about how we can integrate Python into MeTTa and MeTTa back into Python.